So now we're going to take a look at combinations of linearly independent random variables. This is where we have two of the same variable and we want to combine them to find the new mean and variance. If we are having separate variables, that means that we have the first variable distributed like this and the second variable distributed like this. Then we can find the new expected value using this method here and the new variance using this method here. Now, this is different to what we've already had a look at, because previously we've been looking at var of, let's say, 2x, which would be 2 squared var of x. And let's say in this case here that var of x is equal to 3. So here, using the method that we were looking at last time, we would have 2 squared times 3, which gives us 12. Whereas here, using this new method, we would have 3 plus 3, which gives us 6. So it's very important that we understand that if we are counting one thing twice, the same thing twice, then we are using the previous method that we looked at. If we have two of the same distributed items, but they are separate items, then we are using this new method. And it's very important that we are able to spot the difference between them. So we're going to have a look at an example which helps us to see how these two methods differ. So in our example, we have a pack of science equipment contains 3 metre and 2 metre length rods. The 3 metre lengths are normally distributed with a mean length of 3 metres and a standard deviation of 2 centimetres. The 2 metre rods lengths are normally distributed with a mean length of 2 metres and a standard deviation of 1 centimetre. Dave and Karen want to demonstrate a length of 6 metres using the rods from the science pack. Dave decides to use 3 different 2 metre rods, whereas Karen decides to use the same 3 metre rod and mark down the end so that she can use the rod a second time to measure another 3 metre length. And we're trying to find the mean and standard deviation of both of the 6 metre lengths. Now, we have to be careful here for a couple of reasons. Not only do we have the two different situations going on with Dave and Karen, but we also have two different measurements. We have metres and we have centimetres. So what I'm going to do is I'm going to use metres for everything. So I'm going to say that my 3 metre length rods are, I'm going to say that they're X, follows the normal distribution with a mean length of 300 centimetres and a standard deviation of 2 centimetres, so that would be 2 squared. Then we have the 2 metre rods, which I'm going to say follow Y distribution, and they're going to be normally distributed with a mean length of 2 metres, that's 200 centimetres, and a standard deviation of 1 centimetre. So then we have Dave. Now what Dave is doing is that he's getting one of the 2 metre rods, so we'll call that first rod Y1. Then he's getting another of the 2 metre rods, we'll call that rod Y2. And then he's getting a third of the 2 metre rods and we'll call that one Y3. These are 3 separate 2 metre rods, which means that when we're finding the distribution of them, our expected value is going to be the same as the expected value of Y1 plus the expected value of Y2 plus the expected value of Y3. Which would give us 200 plus 200 plus 200, which gives us 600 centimetres. For our variance of Dave's 6 metre rod, we're looking at the variance of y1 plus y2 plus y3, which is going to be the same as the variance of y1 plus the variance of y2 plus the variance of y3, which gives us 1 squared plus 1 squared plus 1 squared, which gives us 3. So Dave's 6 metre rod is going to follow a normal distribution with a mean of 200 and a standard deviation of √3, because it's asking us to find the mean and standard deviation. For Karen, on the other hand, she's using the same 3 metre rod twice. So that is a big difference. She's not got separate 3 metre rods. She has the same 3 metre rod that she's using twice. This means that she has the same variability in the rod's length twice. Whereas here, Dave's 3 2 metre rods could all be varied in different ways. So when we're finding the expected length of Karen's rod, we're going to have the expected value of 2x, which is the same as 2 times the expected value of x, which gives us 2 times 300, which gives us 600 centimetres. For the variance, we have 2 squared var of x, which gives us 2 squared times 2 squared, which gives us 16 centimetres. So Karen follows the normal distribution with a mean length of 600 and a standard deviation of 4. Sorry, I've wrote Dave's down wrong. That should say 600 there from the mean. Sorry about that. So you can see here that we have a big difference. The means are the same, but the variance and the way that we have calculated the variance is different. And there is an assumption here. So the assumption is that these variables are independent, which means in the case of Dave that the length of his first 2 metre rod does not affect the length of his second 2 metre rod, which does not affect the length of his third 2 metre rod. And that's very important, because otherwise we could not use these formulas to help us to find the new mean and standard deviation / variance. So I would now like you to pause the video and give the Now You Try question a go, reading carefully to decide which of these two methods we should use. So hopefully you paused the video and you gave the Now You Try question a go. So here we have OSFC Health and Social Care Department decides to hold showcase events where they can demonstrate the ideas of what they will base one of their courseworks upon. The attendance at these events is known to be normally distributed with a mean of 50 people and a standard deviation of 4 people. Health and Social Care decide to hold 4 such events. Now, in deciding whether we have the same thing 4 times, because they've got to get through so many pupils, it's likely that each pupil only shows their work at one event, which means that each of the events are separate events. It's not that they hold the events so that 4 times as many people can come. It's that they are holding 4 separate events. So that means that if we say that X is our attendance to one of them, that's going to follow a normal distribution with a mean of 50 and a standard deviation of 4, which then means that we are going to be doing X1 plus X2 plus X3 plus X4. We have 4 separate events that are going on. So our expected value is going to be 50 plus 50 plus 50 plus 50, which gives us 200. Our variance is going to be var of x1 plus var of x2 plus var of x3 plus var of x4, which is 4 squared plus 4 squared plus 4 squared plus 4 squared, which gives us 64. So that means that the attendance which I'm calling A, to all 4 of them, is going to follow the normal distribution with a mean of 200 and a variance of 64. So then we're wanting to find the probability that they will receive over 220 attendances throughout the 4 days. So we're looking at the probability that the overall attendance is more than 220. So in our dist, norm, NCD, our lower is 220. Our upper is a really big positive number. Our standard deviation is the square root of 64, which gives us 8. And the mean is 200. And that gives us 0.00621, remembering that this thing at the end here means that we are working in standard form. So, not only can we have separate events that are similar, but we could have completely separate events that we are having to put together. So if we have 2 normal independent normal distributions, let's say x and y distributed as explained here, then when we're putting these together, we'd have a of x plus or minus by, which would be e of x plus or minus b e of y, which is the same as a of mu x plus or minus b of mu y. And similarly for the variance, but this time notice, because we have a lots of the same x, that's going to be a squared var of x, plus, because we always add for the variance, b squared var of y, which means that we'd have a squared sigma x squared plus b squared sigma y squared. So we're going to have a look at some examples of this. So here we have a machine creates 2 types of balls. The machine produces rubber balls whose diameters are normally distributed with a mean of 5.5 and a standard deviation of 0.08 centimetres. And another rubber ball whose diameter are normally distributed with a mean of 3.2 centimetres and a standard deviation of 0.02 centimetres. What is the mean and the standard deviation of the width of the 2 such balls chosen and placed next to each other? So we are wanting, if I describe the first ball here, the one with a mean of 5.5 centimetres as x, so x follows a normal distribution with a mean of 5.5 and a standard deviation of 0.08. Notice here the units are already the same, so we don't need to change anything there. And then if I describe y, the second type of ball, have it following the normal distribution with a mean of 3.2 and a standard deviation of 0.02 centimetres. Then when I put these 2 next to each other, I am going to have x plus y. So when we are finding e of x plus y, that's going to be the same as the expectation of x plus the expectation of y, which is going to give us 5.5 plus 3.2, which gives us 8.7. For the variance of x plus y, we're going to have the variance of x plus the variance of y. And this would give us 0.08 squared plus 0.02 squared. I'm going to have to use my calculator for this. 0.08 squared plus 0.02 squared. So that gives us 0.0068. So x plus y is going to follow the normal distribution with a mean of 8.7 and a variance of 0.0068. So then we have a machine produces balls whose diameters are normally distributed with a mean of 5.5 centimetres and a standard deviation of 0.08. So notice that this is the same as our x. So we're using the same balls as x. So I'm going to reuse that letter here. Follows normal distribution with a mean of 5.5 and a standard deviation of 0.08. The balls are packed into tubes with an internal diameter which is normally distributed with a mean of 5.7 and a standard deviation of 0.12. So I'm going to call this T for tube, follows a normal distribution with a mean of 5.7 and a standard deviation of 0.12. What is the probability that a rubber ball selected at random will not fit in the tube? Now, if the ball does not fit in the tube, then that means that if I did the diameter of the tube minus the diameter of the ball, that's going to give me a value that is less than 0. Because if the tube was bigger than the ball, 1, it would fit. And 2, that would then give me a positive number. But I'm wanting it so that the ball does not fit in the tube. So I'm wanting t minus x to be less than 0. So to begin with, I need to find out what this distribution is. So I'm looking first at what the expected value of t minus x is, which is going to be the same as the expected value of t minus the expected value of x, which gives me 5.7 minus 5.5, which gives me 0.2. For the variance of t minus x, remember that we always add for the variance, so that's going to be the same as the variance of t plus the variance of x, which gives me 0.12 squared plus 0.08 squared, which gives me 0.0208. So that means that we know that t minus x follows the normal distribution with a mean of 0.2 and a variance of 0.0208. So then when we are finding our probability that t minus x is less than 0, so we're going to go back into stat, dist, norm, NCD. So the biggest that we want is 0, our upper is 0. Our lower is going to be a really big negative number, so minus 9999999. Our standard deviation is going to be the square root of our variance, which is 0.0208. And our mean is going to be 0.2. And that gives us 0.0828. So that means that about 8.28% of the balls are not going to fit into the tube. Again, we have the same assumption that these are independent of each other. So the size of the balls are independent of the size of the tube that has been made to house them. So I'd now like you to pause the video and give the Now You Try question a go. So hopefully you paused the video and you gave the Now You Try question a go. So here we have, to get to college, Rehan has to get a bus and a tram. The bus journey is normally distributed with a mean of 10 minutes and a standard deviation of 2 minutes. The duration of the tram journey is normally distributed with a mean of 15 minutes and a standard deviation of 3.5 minutes. Find the expected length and variance of Rehan's trip to college. So he gets the bus and the tram, so we're going to have to add those together. You can see here on the right hand side, I've just written down the distributions that we were given in the question, just so I knew what I was using. So for the expected value of the tram, the expected duration, of the tram plus the bus is going to be the expected duration of the tram plus the expected duration of the bus, which gives us 25 minutes. And for the variance of the tram plus the bus, that's going to be the same as the variance of the tram plus the variance of the bus, which gives us 2 squared plus 3.5 squared, which gives us 16.25. So the tram plus the bus duration is going to follow the normal distribution with a mean of 25 and a variance of 6.25. So then we have to find the probability that Rehan's bus journey takes longer than the tram journey. Now there was 2 different ways that you could have done this. You could have done the bus minus the tram, because you're wanting the bus to take longer. That's going to be a big number minus a smaller number, so that's going to be bigger than 0. Or you could have done the tram minus the bus, bearing in mind that you want the bus to take longer, that would be less than 0. You should end up with the same probability in the end, but your expected value will be different. Expected value of tram minus bus would be the expected value of the tram minus the expected value of the bus, which would give us 15 minus 10, which would give us 5. Your variance, though, for the tram minus the bus should still be 16.25. And then you would be looking at the probability that t minus b was less than 0. And it should give you the same value. That's completely fine. They are the same method. It's just that you've looked at it a different way round. So remember, whatever the sign is, you actually do that with your expected values, but you always add the variance. Now, this is where a lot of people make a lot of mistakes. You always add the variance. Nothing is going to make it so that your data is less spread, other than multiplying by a fraction, but even then, you're not thinking of it in that way, okay? You keep the methods the same. So if we're adding these two sets of data together, then we are going to be adding their variances together. If we're going to be taking these two sets of data away from each other, then we are still adding the variances, which gives us 16.25. Then in our calculator, if you've done it this top way here, b minus t, the smallest value that we want this time is 0. The biggest is a really big positive number. Our standard deviation is going to be the square root of 16.25, which gave me this number here. And our mean is minus 5, which gives us this value here. Just to show you, it does give you the same value if you do it the other way around. This time, if our lower is minus a really big negative number, and our upper is 0, and this time our mean is 5, ta-da! We end up with the same value if we had done it this purple method down here. So just another really important thing to point out, and it's another common thing that people go wrong on, we can only combine together the variance. We cannot combine together the standard deviations. So you always have to work in terms of the variance. So you'll notice when we've been doing questions, if I just go back a page, all the time, even though I've been given the standard deviation in the question, when we've been finding the new variance, we have been combining them. Even when we've been asked to find the standard deviation, you have to find the new variance first and then square root that to find the standard deviation. And if you think about the basic maths behind that, just going to add a page in here to show you what I'm talking about. If we had, let's say our standard deviations were 3 and 2, and we combine them together to make 5, that would mean that the variances would be 3 squared plus 2 squared, which when we combine them together give 13. The square root of 13 is not 5. Okay, these are not the same methods. So you need to be really careful when you're doing your working that you are always working with the variance, not the standard deviation. So make sure that you are looking out for that. You always add your variance, and to look out for whether you have the same thing multiple times, or if you just have the same type of thing. For instance, the health and social care displays, or the rod lengths, when we had Dave using 3 different rods even though they were from the same distribution. You have to be careful with those versus using the same thing more than once. Thank you very much for listening.